So this video outlines the basis of a chi-squared test for independence between two categorical variables. As we know, the joint distribution of two categorical variables can be nicely displayed using a contingency table such as this. And we can do a chi-squared test on 2x2 contingency tables, and we can also do chi-squared tests on larger contingency tables with more rows and more columns, or more categories, such as in this 3x3 contingency table. In the case of a 2x2 table, a chi-squared test will give exactly the same result as a z-test for an effect measure such as an odds ratio or a relative risk. The chi-squared test is often called a test of independence because it assesses whether the distributions in the rows and the columns are independent, or whether knowing the value of one variable will tell us something about what the value of the other variable is. Now this is exactly the same as assessing whether the two variables are associated or not. So when we have more than two rows or columns, for example in a 3x3 table such as this one here, we're testing whether there is a general association, and this will become clear if we look at how the test statistic to perform this chi-squared test is generated. So let's look at this example a little bit more, and it's from chapter 17 of Kirkwood and Stern. So this table shows the results from a survey to compare the principal water sources in 3 villages in West Africa. The frequencies represent the number of households in each village using either a pond, a river or a spring. Now we want to know if there is an association between water source and which village a household is from. So a chi-squared test compares the observed numbers in each of these cells with what would be expected if there was no relationship between these two variables, or if they were independent. So overall, 70 out of 150 households use a river as their water source. So if there was no association between water source and village, then we would expect this same proportion or percentage of river usage in each village. So we can calculate the expected numbers as the proportion of river users, which equals 70 divided by 150 here, multiplied by the number of households in each village. So for village A, this is 50. For village B it's 60 and village C is 40. And this basic procedure can be done to calculate the expected number in each of these cells as if the two variables are independent, and we get the following expected numbers. So a test statistic is then calculated that is based basically on summing the differences between the observed and expected numbers in each of the cells. Now you don't have to remember this formula. A software program can remember it for you and can perform it for you, but it's just here so that you can gain a feeling for what underlies a chi-squared test. This test statistic follows a chi-squared probability distribution if the null hypothesis that the two variables are independent is true. And you can think of a chi-squared distribution in exactly the same way as we've talked about for the other probability distributions, such as the normal, the t, and the binomial distribution. They are all theoretical sampling distributions. So the chi-squared distribution is defined by its degrees of freedom, just like the t distribution, only this time the degrees of freedom is the number of rows minus 1 multiplied by the number of columns minus 1, which sort of makes sense because it represents the number of cells that are freely estimatable or freely subject to variation. You can see what a chi-squared distribution looks like for various degrees of freedom here. So the more degrees of freedom, then the bigger the contingency table, and then the more cells there are subject to variation, and hence the more spread or variation we'd get with our chi-squared test statistic under the null, because it's based on summing the observed minus expected. So the test itself follows all the principles of hypothesis testing that we've described previously. So going back to our example, we get a chi-squared test statistic of 3.54, and we compare that to the chi-squared distribution with 4 degrees of freedom to calculate our p-value, and we get a value of 0.47. So this is a probability of getting a test statistic this extreme if the null hypothesis is true and there is no association between water source and village. So this is a big p-value, and that indicates that there's no evidence against the null. So household drinking source and village appear independent. That's summarised there. And just a couple of things to note: there's no concept of one or two tailed tests with this chi-squared test. That's just the nature of a test of independence for categorical variables. And also note that this is just a hypothesis test. It tells us nothing about the size of association. It just tells us about the strength of evidence against the null that the two variables are independent. To make inference on size, we may want to calculate a set of odds ratios or risk ratios along with their confidence intervals. And lastly, note that the test is an approximation, just like the normal approximation. It's exactly the same. And so it comes with conditions for its use. One condition is that no more than 20% of the expected values in the contingency table are smaller than 5. And if they are, then we might not get a valid p-value. And unlike for 2x2 tables, there's no Fisher's exact test or continuity correction. So if the above condition is not met or is violated, then one option is to group the categories to make the numbers in each cell a little bigger.